Hi goers, welcome to the Chapter 2 review video. So today we're going to be talking about alkanes and cycloalkanes. We're going to talk about their nomenclature, types of isomerism that we see with them, and all of their properties. So before we can even start, what is an alkane? Well, an alkane was a functional group that we saw in Chapter 1, but more specifically, it's known as a hydrocarbon, meaning that it's composed all of hydrogen and carbon atoms. And it has the molecular formula, or general scheme, I guess, CnH2n plus 2. All right, and we'll talk a little bit more about that formula. In addition, it's also said that alkanes are completely saturated with hydrogens. And what does that mean? Well, if we kind of look at this molecule below, before not even naming it or anything, at every given point in this molecule that could possibly have hydrogens, it will have hydrogens. So we said that carbon's bonding pattern likes 4 bonds, right? So a carbon atom in this molecule is going to have the maximum amount of hydrogens bonded to it that it can. So for this carbon over here, carbon likes 4 bonds, and there's already 1 carbon bond, so that means that there's going to be 3 possible more bonds to hydrogen to make that 4 bonded configuration. Okay, so that's just kind of a little bit of, alkanes and their types of bonding. The CnH2n plus 2 rule basically just tells us that for every carbon in this molecule, where however many carbons is n, so if I said 5 carbons, then the H2n plus 2 rule is just going to say that there should be also 12 hydrogens present. All right, so that's just a quick way to kind of figure out molecular formula. All right, so some sort of properties with alkanes and cycloalkanes. Well, alkanes have this really unique property where there is rapid interconversion around their sigma bonds. So if we just took, this molecule ethane, so ethane looks like this. So what could happen is that around this carbon-carbon sigma bond, we can rotate in 3D space, and we can change the location of those substituents. So that's just a really unique property of these sigma bonds and alkanes, is that we have rapid interconversion, and we're going to see that come into play when we talk about stereoisomerism. Okay, so the first thing let's just talk about is nomenclature. So there's a whole, packet of guidelines in your notes to follow these things. So we're just going to do some practice today and, get those concepts down. So let's just start with number 1. So provide the complete IUPAC name for the molecule depicted below, and that's the same for all of these molecules. So whenever we see a plain carbon chain, we want to find the longest carbon chain, meaning just count how many carbons that are here. So it's 1, 2, 3, 4, 5, 6, 7. Okay, so 7 gets a special prefix, hept, H-E-P-T, and we just add ane at the end to indicate that it's an alkane. So this is just plain heptane. All right, that's easy. Let's move on to 2. So provide the IUPAC name for this molecule as well. So we want to find the longest parent chain. So that could be one of two numbering configurations. 1, 2, 3, 4, 5, 6, 7. Or I could have said 1, 2, 3, 4, 5, 6, 7. So they're all going to be 7 carbon chains, but more specifically, which one is right, black or red? And the answer is it's the red one. The red one is correct because whenever there's a substituent or some sort of group attached to the parent chain, that's going to want to get the lowest possible number in terms of priority. So instead of getting 6, which it would if we went the black method, or 2, which we would get if we went the red method, we can clearly see that having a 2-methyl group versus a 6-methyl group would be better. So we're gonna name it as such. So substituents go in front of the name. So we would indicate the position of that substituent like this: 2-methyl, and this is a 7-carbon chain. So we can just add the word heptane, and it's all one word. 2-methylheptane. Okay? I think it's pretty easy with one substituent. Let's move on to 3. So for 3, you have this molecule below, and, we can think of 2 numbering schemes again. So we can think of, let's see, we want to find the longest carbon chain. So let's think 1, 2, 3, 4, 5, 6, 7. That's one possible way to do it. Let's think maybe 1, 2, 3, 4, 5, 6, 7. That's another way to do it. And I do see one more, so we could have done 1, 2, 3, 4, 5, 6, 7, 8. Okay, so clearly the longest carbon chain is going to be the one that goes to 8, so we're going to use the blue numbering scheme. Okay, so if I wanted to name it as such, we would see that we have a methyl group, 2 methyl groups, one on carbon 2 and one on carbon 6. So that would be 2,6-dimethyl. Okay, and we have no other substituents present, so then we can just continue with the rest of the name. So 8 is oct, and we would say ane. So something unique about this is that we use the prefix di. We use the prefix di, tri, tetra, whenever we're dealing with more than one of the same substituent. Okay? So remember, we use the blue numbering scheme here because we got to 8 carbons. So just be cognizant of finding the longest carbon chain. So this was the numbering scheme. 1, 2, 3, 4, 5, 6, 7, 8. Okay? Okay, so we have this molecule below. So again, we want to find the longest carbon chain. So we can start either from here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Or we could have started from the top. So let's think about it like that. 1, 2, 3, 4, 5, 6, 7, 8, 9. So which one would be the right one, black or red? Well, the first substituents encountered first for the black numbering scheme would be at position 3, and for red, it would be 4. So clearly we want to go with the black numbering scheme. So I'm just erase these numbers. Okay, and then we're just going to indicate the position of those substituents. So we have 3, 3, and looks like at 6, trimethyl. And this is 9 carbons, so that's non-ane. Okay, so 3, 3, 6, trimethyl non-ane. All right? Okay, let's keep going. So over here, provide the complete name. So we want to find the longest carbon chain. So if we're thinking about that, it looks like maybe if we started up here, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's one way. Or we could have done maybe 1, 2, 3, 4, 5, 6, 7, 8, 9. So for the black numbering scheme, it looks like we encountered our first substituent at 3. And for the red numbering scheme, we also encountered our first substituent at 3. So now we have to think. So clearly both numbering schemes would be great, but we want to think about maybe some other rules that would make something better. So if the first substituent encountered first is the same number, the next thing we want to say is, are the substituents encountered having the lowest possible numbering scheme collectively? Meaning, are all of those substituents out of the lowest number possible, not just the first one I encounter? So if we did the black one, we see that we have a 3, a 4, and a 7. So 3 plus 4 plus 7. And if I did the red one, that would be a 3, a 6, and a 7. So 3 plus 6 plus 7. So if I were to add those numbers up, you can clearly see that we would have 14 for the black numbering scheme, and then for the red numbering scheme, we would have 16. So since the black numbering scheme gives us collectively the lower set of numbers, we're going to go with the black one. Okay? So if we were going to go with the black one, the name would be something that looks like this. Okay? So we have an ethyl group at 7 and 2 methyl groups at 3 and 4. So ethyl is before methyl, so we need to alphabetize. So that would be 7 ethyl, 3, 4 dimethyl, nonane. Okay? So I hope that helps with this one. This one was a little bit more tricky. All right, so number 6, provide the complete IUPAC name for this molecule. So for monosubstituted cycloalkanes, you don't have to number it because there's only one substituent, and we don't have to have a number in the name because we're just going to assume that the carbon number 1 is the carbon that bears that substituent. So, it's assumed that that is carbon number 1, so you really just have to say that this is methyl cyclopentane. Okay, so methyl indicating the substituent at carbon number 1, cyclo indicating that it's a ring, and pentane that it's 5 carbons. All right, so I hope that makes sense. Let's move on to the last two. So let's just some detour things real quick. Some common names. We have these 4 common substituents that you should be aware of. Isopropyl groups. So isopropyl groups look like Y's. So like that. And the squiggly line just means the rest of the molecule. Isobutyl looks something like this. Okay. Sec-butyl looks something like this. Oops. And tert-butyl looks something like this. Okay, so just be cognizant of those if you see those types of configurations in the molecule, where you can name them with these common names. But you could also do it with their condensed form as well. So I bolded these letters here to understand, how you alphabetize them. So isopropyl and isobutyl, you're going to alphabetize based on the I. That's easy. But for the ones with the hyphenated names, you're going to go based on butyl with the B, not sec or not tert. You're just going to go by the B. So if you had, I guess, ethyl versus sec-butyl, you're going to put sec-butyl before the ethyl. Okay, so just be cognizant of that. So in 7, complete the IUPAC name for this molecule. So it's tricky. I wrote that at the bottom, so let's kind of think about the numbering schemes here. So maybe if we started up here. 1, 2, 3, 4, 5, 6, 7, 8. I like that numbering scheme. What about maybe trying this one in red? What about 1, 2, 3, 4, 5, 6, 7? Nope, that one clearly doesn't work. So, at first glance, you see these kind of common groups. So I see a tert-butyl group over here, and I see a isopropyl group over here. So it would be, I guess a first instinct to just label the carbon chain horizontally in this manner. But remember, we need to find the longest parent chain. So that could include, using that substituent and starting from there, So let's just erase some of this stuff. So clearly the black numbering scheme is the best numbering scheme here because we have the most amount of carbons. So let's get rid of the red. If I were to I guess name this molecule, it would be, we have an ethyl group, we have some methyl groups, so it looks like we have ethyl first. So let's do 4, 6 diethyl. Okay, and then we have 2, 2, 7 trimethyl octane. Okay, so I hope that makes sense on how to name more complex molecules, even though it kind of looks like there's a common name there isn't. All right, so finally we're going to do one more ring. So for these molecules, it might just help to write out the name of the substituent first. So we have a methyl group, we have a sec-butyl group, and then we have an ethyl group. So again, all these rules apply. So I want to number it so that I have my substituents with the collective lowest number of, I guess, configuration. So we can pretty much start with whatever substituent you want here as carbon number 1, but keeping in mind that you want to give them the lowest possible numbers. So, if I started with methyl, 1, 2, 3, 4, 5, it looks like my numbers are going to be 1, 2, and 4. So 1 plus 2 plus 4. So that's going to give me about 7. Right? So now let me think, what if I started with this one? 1, 2, 3, 4, 5. So that was just 5. Okay, so that would be 1 plus 2 plus 4 again. So that's still 7. So now, I guess which one would be better? So we can just pick the better one based off of alphabetizing. So butyl comes before methyl in the alphabet because of the B, so we can just use the red numbering scheme. That would be more accurate than the black one. Okay, so let's erase the black one. Okay, so if I were to name this properly, it would be something like this. 1 sec-butyl, 2 methyl, 4 ethyl, 2 methyl, cyclopentane. Okay, so this molecule is 1 sec-butyl, 4 ethyl, 2 methyl cyclopentane. I know, a mouthful. All right, so I think naming isn't too bad. You just have to know those rules and, find that best numbering scheme throughout these molecules. Definitely be able to do that on a test. Okay, so next, we're going to talk about constitutional isomerism. So, molecules that have the same molecular formula but just differ in atom connectivity is the definition of constitutional isomers. So, alkanes have this, feature of them that we can write many constitutional isomers for them. So, let's just do this example below with hexane. So, draw all possible constitutional isomers. So, when I'm doing this, all I do is basically find the end of the molecule, meaning this methyl group. And I'm going to take that methyl group off, and I'm going to just move along the chain and put that methyl group on carbons throughout the chain and just see if it looks different. So something like this. If I were to take that methyl group off and I were to put it on this carbon, would it be a different molecule? Yeah, so that would definitely be one constitutional isomer. If I were to take that methyl group off that I put there and put it here, would that be another molecule? Yes, it would. So that's basically what we're going to be doing, and we're just going to try a whole bunch of combos. So if I were to take this methyl group off and put it on top of that carbon, the resulting structure would look something like this. Okay, so that would be one of the constitutional isomers. Now, instead of there, what if I moved that same methyl group and I put it on that carbon? Would it be something different? So let's see. Okay, that would work. And now, instead of that middle carbon, what if I put it over here? Well, that would look something like this. Ooh, is that the same? No, it's not, because see how it's the same thing as that one. So this we can't draw because it's the same thing twice. And then, if I were to just put it at the end of the molecule, I'd end up with something that looks like this. But that is really just the same thing as my starting material, just flipped over. So clearly that would not be something we would want to draw. Okay? So the next thing we want to do is consider maybe removing an ethyl group. If I were to move an ethyl group and take that off, what would it look like? Okay, that's valid. That looks good. So if that was basically me taking this ethyl group and putting it there. So now, if I took that ethyl group and I put it here, what would it look like? Just move over. Okay, so clearly that's the same thing as this starting material, so no, we can't do that one. And if I were to put it at the end of the molecule, you can see how it's the same as the starting material, so that wouldn't work. So now let's consider taking a 3-carbon chain off, a propyl group. So taking a propyl group and, maybe putting it there would be something like this. 1, 2, 3. So that's just the same thing as my starting material, just with an awkward angle, so no, that wouldn't be something. And what if I put it, maybe here? So let's see what that looks like. 1, 2, 3. Oh, that's something I have seen before. That looks like that starting material. So nope, that's not a new one. So it looks like we kind of ran out of all of our different types of combos. Yeah, so basically all you want to do is just take little pieces of a molecule off at a time and put them on different locations to see if there are any other, constitutional isomers of them. And you cannot draw the same thing twice. So that's how I would have approached these problems. All right? So conformational analysis. So stereoisomers are molecules that have the same molecular formula and atom connectivity, but they just differ in their 3D arrangement of substituents. Okay? So they have that same molecular formula, but now those substituents could be differently placed around that molecule in terms of 3D space. So I guess over here this might be confusing with the same atom connectivity. They have the same atom connectivity in terms of the molecular formula, but how those atoms are arranged in 3D space is what's differing. Okay, so I hope we're kind of clear on that. So conformational isomers is really a subclass of stereoisomers, which refers to these 3D molecules that are differing just based on rotation, okay? So stereoisomers, big class of isomers where 3D arrangement is the topic, and conformational isomers is a subclass of that where the 3D difference is just based on that rotation. So I hope everyone's a little bit clear on that. So the first thing that we're going to talk about is Newman projections, and it's a way to depict alkanes based on their rotation, in 3D space. So I took this clip from your book. So this is an example of ethane, so it's C2H6, and we can see that this is the, trans view of it. So if I were to draw this, in the Nada projection, it would be hydrogen, 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 hydrogen. Okay, so this is the current side view that we would see, All right. So what's happening is that you can see that the book is taking that molecule and rotating it 90 degrees so that we're putting it in plane of sight. So this is now going to go over here. That's the back carbon. And this is that front carbon. So if you can see, we're kind of turning it almost end on. And then if we do it completely turned on, it looks like this kind of eclipse conformation. So this is that first carbon. So I'll put a dot to, kind of symbolize that. And then the back carbon is this one. Oh, and you can't even see it. It's just that like rim around that front carbon atom. So, when we're looking at a head-on view, you kind of can't really see that back carbon. It should be eclipsed. Okay? So when we do that, we get something that looks like this. This is the Newman projection. So that dot in the middle is this carbon. All right, that's the front carbon. And the substituents attached to that front carbon are those obvious lines right here. So those 3 hydrogens are those 3 hydrogens. And then that back carbon, which we can't really see, that rim around it, that's what this circle is. And those are the substituent coming off the back carbon. All right, so hope that kind of makes sense on how we got from that line angle notation, I guess, to the Newman projection. So now let's look at an example of these Newman projections. So for part 1, it says provide the complete IUPAC name for the molecule depicted. So it looks like just a plain carbon chain, so if I were to number it as such, we clearly get a 6-carbon chain, so that would be hexane. Okay, so now let's just draw all possible, Newman projections for this molecule, given that we're looking through carbon 3 and 4. So maybe it would help if I drew in their hydrogens here. Okay, so if I were looking, so my first carbon is carbon 3, and my last carbon is carbon 4. So let's just draw the Newman projection in that current orientation. Okay, so the dot is my first carbon, so we clearly have an ethyl group going up. And we have a hydrogen to my left and to my right. And on the back carbon, we have the hydrogens to the left and to the right. And then we have an ethyl group coming down. Okay, so that would be the Newman projection in the current conformation that it's in. And if I were to draw the remaining Newman projections, the only way that I would do that is by keeping one of the carbons constant, and then the other one I would just rotate 60 degrees at a time. So let's just say I'm going to keep the front carbon constant. Okay, so let's just draw that in. And there's no reason that I picked the first carbon. You could have picked the back carbon as well. If I were to rotate that back carbon 6 degrees, the substituents would look something like this. Okay, so that would be a result of a 60-degree rotation around this back carbon. So if I were to take, this group and move it 60 degrees, this would be the result. And you want to keep doing that until you've done everything. So let's just go back to black. Let's keep that first carbon the same that it was, so the ethyl group going up. Okay, and if I rotated the back carbon one more time, 60 degrees, we would see that we have this structure. Keep going. So if I were to keep that first carbon the same and rotate again, okay, that would be that. And if I kept going, let me do this down here, I guess. And if I kept going one more time, so those are my 6 Newman projections based on rotating that back carbon 60 degrees each time. Okay, so notice that I kept the front carbon the same, so all that changed was rotating that back carbon, and you should always have 6 total structures. Okay, so the next part is going to say, Label each of the above Newman projections with their proper name if applicable. So let's just give these names. So where the first picture that we drew it, where the ethyl group and the other ethyl group, or the two largest groups, are 180 degrees apart, this gets the special name of the anti-conformation. Okay, so let's highlight that. That's the anti-conformation, and that's the most stable Newman projection because those two largest bulky groups are as far away as possible. Okay, so for the next structure, we see that we have, these eclipsing interactions with the ethyl and the hydrogen, as well as a hydrogen-hydrogen interaction. So it's fitting that we give this name the eclipsed interaction. So eclipsed. Okay, and there's significant energy barriers with eclipsed because we see that those ethyl and hydrogen groups, or those hydrogen and hydrogen groups, are going to interact because they're literally on top of each other in 3D space, and that's not favorable. Okay, so if we keep moving, we see that we have our two largest groups, pretty much adjacent to one another. More specifically, they're 60 degrees apart, so we give this conformation a special name called the Gauche conformer. So Gauche, Gauche conformer. All right, this is also, not a favorable conformation because those two large bulky groups are pretty close in proximity, but, it gets a special name called Gauche. All right, so if we keep going, so in this conformation, we have specifically the two largest groups eclipsing with one another. So this is an eclipsed conformation, but it gets a special name called totally eclipsed. Oops. And it's called totally eclipsed because the two largest groups are totally on top of each other. All right, so if we keep doing the remaining, so this conformation is just another version of the Gauche. It's just with the ethyl group on the right instead of the left. So we can call this one another Gauche conformer. Okay, and down here, we have another one of those eclipse interactions. So we can just say eclipsed. And I just wanted to make a note that you could also call the Gauche staggered conformers. They are staggered conformers as well because, all the substituents are staggered from one another. So maybe in red I'll just write, you could have said staggered. But we really want that specific name of Gauche because this is a situation where the two largest groups are 60 degrees apart. Okay? So now rank all the Newman projections based on their relative torsional strains. So let's think about, the relative stability, so maybe I'll change to pink. So we said that the anti-conformer is going to be the most stable conformer because the anti-conformation is the one where those two largest groups are as far away as possible. They're 180 degrees trans, and that's the most favorable. We don't have any of that steric hindrance. So this is definitely going to be the best. So I'll just say that number one over here, number one equals smiley face. So that's the best one. So we have number one. Okay, so the next best ones would be the ones that don't have any eclipsed interactions. So we're thinking about the two Gauche conformers because in those situations, there really isn't, any sort of steric clash or steric overlap. Yeah, they're close in proximity by being adjacent, but they're not directly on top of each other. So the two Gauche conformers, we'll just say 2A and 2B, would be fitting for the next ones. Okay, those are equal in energy. So the next one would be, one of the eclipsed interactions. So we have, in the blue over here, we have an eclipsed ethyl with a hydrogen. And then the black one at the bottom right over here, that's an eclipsed ethyl and a hydrogen as well. So it makes sense that those would be equal. And then the last one is a totally eclipsed. So we said that totally eclipsed is the worst conformer because those two largest groups are directly on top of each other. That is the worst thing that you could have. So this is why we're going to say that the two eclipsed conformers are 3A and 3B, because those are equal in energy. And finally, that totally eclipsed is the worst, number 4. All right? So be prepared to, rate any of these conformers out on the test, name them, and then rank them. Okay? So it makes sense that the given orientation, or the trans orientation, excuse me, the trans orientation is the most favorable because those two large ethyl groups are as far away as possible. And that's actually why when we teach you guys to draw a line angle formula, you start like this, in that pattern, because that specific conformation of alkanes is the most stable. Okay, cool. So let's move on to chair conformers. So let me just erase some things over here. Okay, so chair conformers. So chair conformers is a specific, feature to cyclohexanes. And it's due to the fact that there's significant ring strain based on it being in a cyclic molecule. So this molecule has adopted this 3D configuration to, I guess, minimize the amount of steric strain with substituents, okay? So I drew in a couple of these diagrams myself, and I have something from your book here, because I think the visual is really important for figuring out how to draw these conformers. So for the chair, let's just say that we have this planar cyclohexane molecule. So nothing special, I just numbered it 1 through 6, all the way around the ring. And I drew in a wedge and a dash on both carbon 1 and carbon 4. Let's just say, we can say that they're methyls, but I just meant to show that there could be substituents there. Alright, so what's going to happen is I'm going to take carbon number 1 and pull it up out of the plane, and also while I do that, I'm going to take carbon 4 and pull it down under the plane. Okay? So the result of that move would be something that looks like this. Alright, so maybe I'll just zoom out a little bit. So you can see that the original plane I have in dashed lines. So that's 2, 3, 6, and 5. So those carbons we didn't touch, so those should stay in plane. But you can see how carbon number 1 is clearly puckered up above the plane. That's what happened from that move. And carbon 4 over here is now below the plane, which you can see down there. I hope that visual kind of makes sense of how we got the first chair conformer. Okay, so I'm really just taking carbon 1, pulling it up, and taking carbon 4 and pulling it down. All right, so that's how you got this chair conformer. So what happens is that this is the results of that move. If I took carbon 1 right here and pushed it up, and carbon 4 and pulled it down. But what would happen if I said, I wanted to take carbon 1 and pull it down, and carbon 4 and pull it up? Okay, so the result would be a structure that looked like this over here. So this is the ring flip. So that's all that's happening in a ring flip. So instead of taking carbon 1 and pulling it up, and 4 and pulling it down, I decided to take 1 and pull it down, and 4 and pull it up. So you can see now if I drew like the original plane, it would be, these atoms, excuse me. So 2, 3, 5, and 6. Okay, so those all still stay in plane, but now this was carbon 1, so now that's below the plane, and carbon 4, that's above the plane. So that's how we're getting these ring flip conformers. Okay, but I want to also point out one other thing, that you can see that the substituents labeled A and the substituents labeled C are both axial, meaning that they're going perpendicular. Okay, so A and C are both axial. So then you can see in the ring flip, ooh, now they're not up and down, now they're equatorial. So in a ring flip, always note that axial substituents are going to go to equatorial substituents, and equatorial substituents are going to go to axial substituents. Okay, so that's another common feature of a ring flip. Okay, so now that you know that there is, this is how the chair conformers form, and the substituent effects of that changing during a ring flip, let's look at, stability. So if I were to give you a monosubstituted cyclohexane, such as, methyl cyclohexane, which chair conformer is better? So chair conformer 1, all I did was take carbon 1 and pull it up, so that's this one, and carbon 4 and pull it down. So the result of that move would be this structure, all right? And if I were to do the opposite of pulling carbon 1 down and carbon 4 up, then that would give me something like this, okay? So which one is more stable? And the answer is it's chair number 2. So chair number 2 is more stable because of something called 1,3 diaxial interactions. So if I were to look at that methyl substituent, and I called that carbon number 1, at position 3, both position 3s relative to the methyl, there's going to be an axial up hydrogen that it interacts with in 3D space. And that is significant, I guess, a significant energy barrier to be having this conformation at equilibrium. Because carbon 1 and carbon 3 are both axial up, and they're very, very bulky and can interact with one another, and it's very repulsive. So you're not going to see a lot of, chair number 1 at the equilibrium due to the fact that there's this 1,3 diaxial interaction. When I look at, chair number 2, you can see that that methyl group is now equatorial, and equatorial substituents do not observe 1,3 diaxial interactions, so there's really no energy barrier at, chair number 2. So we would have a lot more of chair number 2 at equilibrium than, chair number 1. Okay, because it's due to that fact that axial substituents have something called 1,3 diaxial interactions, and equatorial groups don't have that at all. Okay? So, a really cool depiction from your book is that example of methyl cyclohexane. So, if we looked at the two relative chair conformers, so this is that methyl group, that's CH3, so C and the H's. So that's CH3, and that's at the equatorial position. So you can see that it's really kind of oriented away from the chair and not interacting with anything. So we like that. And then if you were to look at, this conformer over here, where it's axial, this is the CH3 group. And you can see that the hydrogens, since it's so bulky, are going to interact with the other axial hydrogens, and it's going to cause significant energy strain. So that's why the book actually uses these equilibrium arrows, where it shows that, this chair conformer where the CH3 group is on the equatorial position is definitely the most stable, or there's more of it at equilibrium due to the fact that we have minimized these diaxial interactions. So that was pretty much a lot of theory about chairs, so let's just use an example below. So the molecule 1s3s1-chloro-3-ethyl cyclohexane, mouthful, is depicted below. So draw both chair conformers for this molecule. All right. So when you're doing that, you can pick any carbon as carbon number 1. So I'm just going to pick, the top carbon to be carbon number 1. Okay. And I'm going to draw both of my chairs. So first I'm just going to draw this one over here. Oops, excuse me. Okay, and I'm going to draw the other one over here. Okay, so I'm just going to start with the one over here. If I were to say, number around the ring, 1, 2, 3, 4, 5, 6, okay? So remember what we did in our moves. Carbon number 1 in this depiction is clearly up and above the plane, and carbon 4 is clearly down and below the plane. So on carbon number 1, we pulled that thing up. So the wedge thing on carbon number 1 should be sticking up. So is that group on carbon number 1 the wedge? No, it's on a dash. So that must not have been the axial thing there. So that has to be the equatorial group. CH2, CH3. All right? So the axial thing would have been that hydrogen, which is on a wedge, because that was what was pulled up. Okay? So 2, there's nothing really important, but 3 there is. So the trend is always axial up, down, and up. So at carbon number 3, we need to be up. So does that stereochem on substituent number 3 match the trend of being up? Well, yeah, wedges like being up. So we definitely have a axial chlorine going up. And that's pretty much it. And don't forget that equatorial hydrogen. Okay? So that is the chair conformer for this one. And if I were to do the ring flip, I could either, do it from the starting material, or I could realize that everything that was axial became equatorial, and everything that was equatorial became axial. So that methyl group, CH2CH3, was definitely equatorial. So now it's going to be axial down. Because remember that move of pulling carbon 1 down now, and carbon 4 going up. So that's why we start axial down. Okay, so at carbon number 3, the trend is down, up, down. So at carbon 3, we were axial for that chlorine, so now it's equatorial. Okay, so which chair, I guess I'm getting ahead of myself, indicate with a box which chair conformer would be more stable. Okay, so we want that largest group to be oriented away. So clearly, what is that largest group? We have CH2CH3, or we have just a plain chlorine atom. So clearly the CH2CH3 group is going to be the bulkiest, so this would be the best chair conformer, because that is in the equatorial position, or minimizing diaxial interactions. There still are diaxial interactions with the chlorine and the hydrogen, but not as significant as it would be with an ethyl group and a hydrogen. Okay? So calculate the relative energy strains for each of the conformers. So, let's just do this most stable one first. So we see that the chlorine-hydrogen interaction, so there's 2 hydrogens. So this chlorine-hydrogen interaction is going to cost us 2.2 kilojoules per mole. So how many of those interactions are there? Well, there's 2 interactions, so that gives me 4.4 kilojoules per mole of interactions. Okay? So that would be from the energy of the first chair conformer. And if I were to do the ethyl substituents, we see that there's this ethyl over here and the hydrogen here, but don't forget there's also another hydrogen here. So there also is 2 moles of that. So the CH2CH3 we said was 7.3. So 7.3 times 2 is 14.6 kilojoules per mole. So you can clearly see that the 4.4, or this one, is a lot less energy than, the ethyl groups being on an axial position. And that pretty much summarizes Chapter 2 material. Definitely go over this, a lot of cool key concepts here, and I'll be posting Chapter 3 and Chapter 5 shortly.